I have an emeritus position.
Yeah, so you come here.
I come here every day. I teach. I'm here every day. So
only no teaching.
Yeah. So I'm also an interloper in this conference. I'm an economist. I'm not a probabilist. And in fact, I'll be giving an anti-probability talk showing that you don't need randomization in the problem that I'm going to talk about. I hope you will find the problem interesting and its solution interesting as well. So as I said, so as it's clear from the from the slide, it's joint work with several people. Two of my students, Shomendu and Sonal, my colleague Devashish, and my friend Jay from Columbia. Okay. So
is Jay an economist?
No,
he's an OR.
He's an OR person, but I mean, you see this is. So okay, so here is the problem. There are teachers and there are schools, and each teacher is initially assigned to a school. So that's the place where the guy works. And each school J needs NJ teachers and has an assignment of EJ teachers. Historically, those are the assignments. And now there are surplus schools, EJ, J where EJ is greater than NJ, and there are deficit schools where EJ is less than NJ. And the question is, how do we redistribute teachers to improve this assignment? And what we will show is that there is one good way to do it, only one good way to do it, which satisfies various criteria. Okay, so in economics talks we have to give a lot of motivation and so on, otherwise the paper has no chance of being published. So here are some slides, some motivation slides. So essentially, teachers, schools widely differ in teacher-student ratios, and the right to free and compulsory education in ways to improve our hiring, consolidation, and transfers. So we will be looking at transfers. And here is section 22 of the RT Act in very Sarkari language, which should be familiar to everybody in ISI. Sanctioned strength of teachers in a school shall be notified by central government, appropriate government or local authority. Redeploy teachers of schools having strength in excess of sanctioned strength, etc. Okay, so the main point is that you can be transferred against your wishes. You can just be told you're transferred. But of course, if you do so, then we know that in India there are various ways to stall that by going to court, etc., etc. Right? So it is a good idea to take the preferences of teachers into account. Right? If you don't, then you will have you will face all kinds of difficulties. So, for instance, Haryana has this document 2016. There's a lot of work done on Haryana because they have data and stuff like that on teacher transfers and so on. So, in its vision document, it said the vision is to ensure equitable demand-based distribution of teachers to protect academic interests of students and optimize job satisfaction amongst its employees. So we say that is something to do with teacher preferences, okay, in a fair and transparent manner. So this is essentially a paper on fairness. Yeah. Okay. So about the paper, objectives and main results, we formalize a version of the teacher transfer problem. It's a network flow problem, and so we with dichotomous preferences and define fairness and efficiency of outcomes in a natural and unambiguous way, and show that these fair outcomes can be achieved by a strategy-proof mechanism. So we're using the language of game theory here. So this is a situation where your preferences are private information, so you have to supply them to whoever is the authority which is prescribing transfers. So, and you want to make sure that people have the incentives to be truthful. If they're not truthful, then who knows what happens. So we show that we can actually achieve this by something which is strategy proof. So, each teacher finds their initially assigned school acceptable, okay, because they're there, and teachers can only move to schools that they find acceptable. And so this, again, in the language of economics, we call it individual rationality for teachers. Okay, so here are some special features of the model that teachers can only be transferred from surplus schools, and teachers can move only to deficit schools. You can see that you can do better by transferring teachers among surplus schools and then transferring some of them to deficit schools, right? It's not clear that you may be able to achieve more by transferring, by doing this. It has less constraints, so you'll obviously do at least as well. And it's easy to construct examples where you should allow these transfers between surplus schools, between deficit schools, and between surplus and deficit schools. But we are actually, we prevent this. In fact, we can deal with many of those problems using the same ideas. So, but let's for the moment assume this, that you can only move from surplus to deficit, and no surplus school can become a deficit school, right? Presumably that school will object, and no deficit school can become a surplus school. Okay. So you want to maintain these requirements, and only the teachers initially assigned to surplus schools can move. Okay. Get this slide. So here is a model. A set of deficit schools D1 to DL, a set of surplus schools S1 to SM, and a set of teachers T1 to TL. Each teacher is initially assigned to a surplus school, so it's the owner of the school, O of TI, which belongs to S, and WSJ is the set of teachers initially assigned to SJ. Okay, so this is the problem that you start with. And here is where you take teacher preferences into account. So it's a very simple kind of assumption that each teacher has a set of acceptable schools, acceptable deficit schools. Okay, A of TI, which is a subset of D. And for each DK, so for each deficit school, the beta of DK is a deficit of DK, and we have a deficit vector, beta, which is beta D1 to beta Di, right? So this is the initial deficit vector, and there is likewise an initial surplus vector, right? So surplus schools have, they have a certain endowment of surplus teachers. And so this is a teacher transfer problem. It's this two deficit schools, surplus schools, set of teachers, set of acceptable schools for teachers, and this beta and alpha. So this is the problem. Okay, and so this is what a transfer is, and let me just not go into the notation. Teachers can only move to schools that they find acceptable. No surplus school can become a deficit school post transfers, and no deficit school can become a surplus school post transfers. Those are those 3 bullet points there. Okay, fine. And so, what are our objectives? What are the objectives? So the objectives are formulated entirely in terms of the achievable post-transfer deficits. Okay, so suppose we have some transfer sigma in capital sigma, which is the set of all possible transfers. Then you can compute the post-transfer deficit in each deficit school. Okay, and so as a planner or a bureaucrat or whoever is interested in achieving in selecting one beta from among the set of feasible betas. Okay, and the question that we are addressing is, what are the reasonable objectives of the planner? And what we want to show is that there is a very clear way to define this. Okay. So, I mean, to lead you guys on for a bit, we can say that there could be many kinds of objectives. You could have what we call utilitarian objective. We could want to transfer as many teachers as possible, right? Transfer as many teachers as possible. You could have what's called Rawlsian, right? After the philosopher John Rawls, which is that you want to you might want to minimize the maximum post-transfer deficit. You may want to do it lexicographically. That means when you compare two vectors, you look at the worst deficit, and you want the worst deficit here to be less than the worst deficit there. Then if they are equal, then you go to the next one, etc. If that's equal, you go to the next one, etc. That's the lexicographic objective. You could have a general welfare maximizing objective, which is to minimize the total loss for a continuous and convex loss function of the deficit. You could have some general function, right? General continuous convex loss function. And what we want to show is that there is a single, for this problem, there is a single transfer meeting all these objectives. Okay. And what is that? That is, so in general, if I give you a general problem, you would be very surprised if this were true, right? So, if you are if you are a policy economist, then you would say, okay, a policy which maximizes total income, gross national product, is very different from the policy which, let's say, maximizes the income of the worst off person in that society, and so on, right? These are very conflicting objectives. And what we're trying to show is that in this case, these objectives can be met simultaneously. Okay, and so here's a sort of toy example. So suppose you have to choose beta 1, beta 2 such that 2 beta 1 plus beta 2 is less than 30, then the utilitarian solution is 30, because that's the highest sum, and the lexicographic solution will lie on the 45-degree line, and it's 10, 10. So they are very different in general. So what we show is, put it differently, that in this model, you can find a post-transfer deficit vector which majorizes, or what we call Lorentz dominates, all other feasible transfer vectors. Okay, and so that's what we're going to do. So, so here is the definition of Lorentz dominance. So for every vector gamma, so what we do is this box gamma is the vector where the components are ordered from highest to lowest. And you have Lorentz domination if the partial sums, if all the partial sums in one are less than the partial sums of the other. Not just you order these vectors from high to low, and then what you have are these partial sums which are also go in the same direction, right? So that's Lorentz domination or majorization, and it's well known that Lorentz dominant transfer reconciles the utilitarian, Rawlsian, lexicographic, and welfare maximizing objectives. Now, as you'll see that one of the critical ingredients of our solution here will rely on the work of two colleagues and friends of Rahul, Bhaskar and Devraj. So they called what did they call the egalitarian solution? The lexicographic solution they called the egalitarian solution. So they were here in IISER at that time. Exactly. It was here. By the way, Rahul has some papers in economics journals. He not want to reveal it.
Devraj, yes.
Okay. So here is our theorem. There exists a Lorentz dominant transfer for the PT. That's our result. And our second result is that there is a way to achieve this through a strategy proof mechanism, which I'll come to in a moment. Okay. So what do? We'll provide a roadmap to prove the theorem, because I think the the way to solve this problem may be of some interest. And the point is that a TT problem, teacher transfer problem, can be formulated as a single source, multiple sink network flow problem. Okay. So, so apologies if you guys are, if all this is familiar to you, but let me just perhaps give you an example. So this is, so suppose there are three deficits, three surplus schools, S1, S2, S3. There are, how many? 7 deficit schools. And so there is an edge from S1 to T1, which says that, which signifies that T1 belongs to the deficit school S1. Here T2 and T3 belong to S2. Here T1 and T5 belong to S3. And there is an edge between T1 and D1, which signifies that T1 finds D1 acceptable, right? Similarly, D2 is acceptable for T1, D3, D4, D5 are acceptable to whatever, T2 to T3 and D4, etc., etc. Now, the thing is, the capacity of these edges is important. So there are these node capacities here, which are the deficits of the deficit schools. So there are 7 schools. We start off in this example with everybody having a deficit of 5. There is a source node N0, and this is connected to all the surplus schools, and the capacity of this edge here is the surplus of the surplus school S1 or surplus school S2, S3. So here, for instance, it has a surplus of 2, but and it exactly has 2 teachers who are willing to move, right? But in general, this would have been 1, and so you would have to only allow 1 of these teachers to move. And the question, so so as you can see that a teacher transfer problem is a flow, an integer flow problem in this network, right? So it's a flow from N0 to these edges, to these terminal nodes here, these terminal vertices, and what you want is these flow conservation. I should mention that the capacity of these edges S1 to T1, these are all 1, right? The capacity of these edges are all 1, and the question is, okay. So now the question, so these are a teacher transfer problem is an integer flow problem, and I don't particularly have to define, go through all this notation. It's defined. I've communicated it verbally, and so the question here is about
the domain are integers, right?
the domain is integer, but the way we will solve it
is and everything.
Sorry,
you said everything had to be continuous.
No, that was the objective function. The objective function could be this.
Now the question is here also the number of surplus is not the total number of surplus is less than the total number of deficits. Also.
Yes. So that makes the problem interesting in a certain way. But we are general about this. I should say though that the TT problem is an integer problem, and that's important. And the way we solve it is by considering a relaxed problem where you allow for continuous flows, then prove a result there, and then approximate or round it to the integer problem. So that's really what we're going to do. Okay. So so we have an integer and relaxed flow problem. So script F is a set of integer flows in G, and so gamma I is an integer network flow problem, and every transfer sigma can be uniquely identified with an integer flow problem F, right? So this should be fairly clear, okay? And the way that we will solve this problem is actually to relax the integer flow problem to general flow problem, and so we allow for more than um, integers. And the point is both the integer flow problem and the relaxed flow problem are using the same network G, and the set of integer flows is obviously a subset of the set of relaxed flows, shall we say. Okay, so how do we solve this problem? The first problem that you have to confront is, what is the set of feasible flows? What is the set of feasible flows? Okay, so let me just reiterate what I had said a little while earlier. So step one is to show that there is a flow f hat in capital F hat. So this is the relaxed flow, the relaxed problem, such that the post-transfer deficit resulting from F Lorentz dominates all post-transfer deficit arising from flows in F hat. Then the second part is to round the flow to an integer flow so that F Lorentz dominates all integer flows. Right. So if you do the rounding, you will lose the Lorentz domination property for all flows. But the point is that we still want to do it in a way that will Lorentz dominate all the integer flows. Okay. So the step one, we rely heavily on a classical paper of Megiddo in 1974, and the way to do it is actually to construct a cooperative game from the network flow problem. So what is it that we do? So I mean, in case some of you don't know what a cooperative game is, a cooperative game is just the following object. So you have a set of players, let's call it n, and a function v, which actually assigns a value v of s for every s subset of n. So this is the worth of a coalition S. So give me any coalition. V of S is the worth of that coalition. Okay, and the a very classical notion, a very classical concept in cooperative game is the so-called core of a cooperative game, which is defined by Shapley. So what is the problem? The problem here is to find xi, which is a payment or an allocation to each agent in n, such that the summation this is equal to v of n, and for every coalition this is greater than equal to v of s. Okay, so what you're trying to do is that you're trying to what you're trying to do is to split the value of the grand coalition n to each of these players, such that for any coalition, summation xi is greater than equal to v of s. So another way of saying is that suppose some coalition is being given xi such that it's less than v of s. What they want to say is, why should we accept this? We can come together, we can together generate v of s, okay, and we can do better than what you're offering us. So in particular, I should be able to do better than if I'm on my own, right? So this is the notion of what's called a core of a cooperative game. And the basic transformation of this problem following Megiddo, the basic approach is to show that a feasible flow in the relaxed problem corresponds to a core allocation in a suitably defined cooperative game. Okay? And then what you do is that you try and find the most equal way to solve, to give the most equal way to split v of n satisfying these constraints. Okay, and there is an algorithm to do it, and in fact, it's something that Datta and Reddy did in, although that was not their objective, right? So they were trying to do something else, but what they did was essentially this, and Megiddo also did it. Anyway, so following Megiddo, we construct a cooperative game W, and step 1B, following Megiddo and Dattare, we use properties of W to find a Lorentz dominant flow in gamma R. And then what we do is step 2 is to round this to integer flows such that you still have Lorentz dominance amongst all integer flows. Okay. So how do we define this cooperative game? Here the set of players is going to be the set of deficit schools. Okay, and what is V of S? S is now a set of deficit schools. It is the maximal flow to S. Right? 5 minutes. Okay. I should stop. So okay. So that's how we define the cooperative game, and so that's how we define the cooperative game, and basically. Okay, so this is how, these slides are how to describe the cooperative game. But here is the proposition, and this is essentially due to Megiddo, we have to do a little bit of adaptation for our setting, that a flow is feasible if and only if it belongs to the core of that cooperative game. Right? If it belongs to the core of that cooperative game, that's so this is a characterization of the flows, and that's the summary. A post-transfer deficit vector is achievable if it lies in the core of a game with integer coalition work. And you can show using the 42% algorithm and so on and so forth that these are all integers. These B's that you get. Okay, and the second property is that this cooperative game has a particular structure, which is that this game is convex. In other words, that the marginal value of adding a player or a deficit school, that increase is actually going to be larger for larger coalitions. So if I add a deficit school to a coalition which contains more in a superset sense to a larger coalition of deficit school, then the marginal addition is going to be higher. So it's a convex game. And then we use this algorithm to find a solution which is as equal as possible. I don't really have time to discuss this algorithm, but this algorithm is due to Megiddo and also to Datta and Ray, who are looking at cooperative games. Okay, so here the example does all these computations. The problem is that the solution that you get in the relaxed problem is not necessarily going to be an integer, because you're kind of looking at averages, right? So although the numerator and the denominator are both integers, the ratio may not be an integer. The numerator is the value of a coalition, and the denominator is the size of the coalition. So you don't want to. I mean, if you want to do it probabilistically, we'd say, okay, this teacher spends half his time in this school and half his time in that school, but we don't want to do that. I don't think that would be acceptable. So we want a deterministic solution, and okay. So this is all about the algorithm, and so what is tricky is this integral rounding, and we have examples to show that you cannot round in arbitrary ways because you will end up violating these Megiddo constraints. right? So how do we find the rounding? You actually construct, it as a solution to another network flow problem, an auxiliary network flow problem, fixing the nodes more carefully and so on, and then claiming that the max flow in this problem, which is integral, must actually yield a solution to our original problem. And then the work is to show that this does not destroy the property of Lorentz dominance. So you lose Lorentz dominance amongst all possible transfers into all possible flows. You will lose Lorentz dominance, but the important thing is that you will still have Lorentz dominance amongst all integer flows. Okay, so that is really the point of all this stuff, and these were examples. So I've just given you an idea of the proof. So I'll just end in the last 2 minutes about strategy proofness. So which is, you might say, another sort of game theoretic aspect. So a natural assumption is that the planner will not know, what the acceptable set for a teacher is. Okay, so this has to be reported. And then you must account for the possibility that the teacher will misreport in order to get something better. So here there are only two classes, being transferred to an acceptable set, remaining in your original school, and then being transferred to a place that is not in your acceptable set, right? So what we assume here is that you want to be transferred, right? So that's your acceptable set. Then you want to stay where you are, and then the last class of references is that you don't want to be sent to a non-acceptable school. And what you do is the question is, so if the assignments are based on the reports of of the teachers, is it possible? Can you achieve these Lorentz dominant vectors in a way which does not involve a teacher lying on this representative, right? So and the answer is yes. There exists a strategy proof teacher transfer function, right? And it's not, this part is not particularly deep. I use deep in quotation. I mean, it's just breaking ties in particular ways, but it involves a little bit of work in which you can lie and cheat in all kinds of ways. You can say that something is not acceptable when it is. You can claim that something is not acceptable when it is acceptable, and vice versa, and do all these kinds of tricks, but none of it will help you. Okay, so that's it. All I have to say. So I hope I've managed to give you a sort of a flavor of what this stuff is. Didn't have time to discuss anything in detail, but okay, thank you. And congratulations, Rahul. Yeah, what is it? It's commiserate.
For many of us, it's commiseration, right?
I see. I mean, nothing really changes except that your salary will half. So that is not so nice. But Baki, everything else is.
Yeah, exactly.
So I have one quick question.
Yeah.
So you are not using this kind of probabilistic solutions, but suppose two schools are really nearby,
Yes.
and then if you allow them to say morning working here and afternoon working there, will it be better sometimes? Incorporate
Well,
the
yes,
geography of the schools, etc.
Yes, I mean, if you can split, then then the deficit vector that you will be able to achieve will typically be superior.
But both schools should be in the acceptable set of.
Yes,
Yes, of course.
Yes.
Assuming. Assuming,
And they will be if they are hopefully nearby,
Yes.
unless one is a
I
rowdy
ex-
neighborhood. and-
yeah, exactly.
Yes, yes. So in general, yes.
It's
I mean, in matching theory in general, and you know, in general, allowing tossing coins and doing things is beneficial not just in terms of these objectives, but also also in terms of revealing your private information truthfully. It helps in that as well.
Right.